All right. So, like I said, our course calendar, we'll be doing section 2.5 and finishing up that today and doing 2.6. Also, like I said, on the modules and stuff, where are we at? Well, if you scroll down here to the 2.5, which we started last time, that web work will be due on February the 18th there. But also, we're doing 2.6. You notice that that quiz for 2.6, if you haven't done it yet, it is due tonight by 11:30. Okay? And this 2.7 is what we're going to be doing next class period. So so we're really right on schedule in terms of the way I've got things kind of laid out. And I will find it again. I will see if I can get that course calendar open for you guys. If you can't it seems to be locked or whatever. All right. So let's come over here and let's get started. Now, let's just practice a little bit here. What we've been doing is the last of the big three formulas for calculus in terms of being able to take derivative of really hard stuff. The first one was the product rule. Derivative the first times the second plus the first times derivative the second. The second one was the quotient rule. Derivative the top times the bottom minus the top times derivative the bottom all over the bottom square. The third one, section 2.5, is on the chain rule. Chain rule, the way you look at it is you look at outside, inside. It's some kind of a composite function. You've got an inside part of a function and you got something on the outside. Inside, outsides. And to take derivative of a function that has insides and outsides, you take derivative of the outside, inside stays the same, times derivative of the inside. Now, the hard part comes at the end of section 2.5 when they start to combine a bunch of rules together. And the real trick is to pause, hesitate, and ask yourself, what do you see? So, here we go, right here. I think the last problem Desiree did last time was problem number 18, which was, let's just kind of mark ourselves through it. It was f of x is equal to the cosine of x times the sine of x. You're right, I see a product in here, but what I really see is a cosine on the outside. And remember, with all trig, the angle is on the inside. Cosine is on the outside, and the x sine of x is the angle on the inside. Outside, insides, that's chain rule. Chain rule. You take derivative of the outside. Derivative of the cosine is negative sine. The inside, the angle, x times sine of x stays the same. Then you do times chain rule, the derivative of the inside. And the derivative of the inside, this inside is this x times sine of x, and that times in the middle tells me it's a product rule. Product rule. Derivative of the first times the second plus the first times derivative of the second. Derivative of the first, derivative of x is 1 times the second sine of x plus the first x times derivative of the second. Derivative of sine of x is cosine of x. And then I close my bracket on the outside of that, and that's actually my derivative for the cosine of x times sine of x function. Let's take a look at the next guy. This is a web work problem, and this is how they like to give you web work problems on just kind of, they give you a bunch of different kinds, and here's one of the kinds. They like to give you this functional stuff. Like, for example, big f of x is equal to f of g of x. Little f is on the outside, g of x is on the inside. Where f of negative 7 is 2, f prime of negative 7 is 2, f prime of 3 is 15, g of 3 is negative 7, and g prime of 3 is negative 8. Your mission in life? Find big F prime of 3. Okay? So, before you can find big F prime of 3, you've got big F of x, which is f of g of x. And this is why I tell you guys, now you can memorize the book formula if you want to, but memorizing the words will allow you to derive the book formula when you need it, and that's one less thing you got to have memorized. So, to take derivative of this guy, big F prime of x, you've got to take a derivative of f of g of x. F is on the outside, g of x is on the inside. That's chain rule. Chain rule. Derivative of the outside, that'll be derivative of f. The inside, g of x, stays the same, times the derivative of the inside. Well, the inside's g of x, so the derivative of that would be g prime of x. So that's actually the rule, if you go check your book, of what they call the chain rule. F prime of g of x times g prime of x. Derivative of the outside, inside stays the same, time derivative of the inside. So now, they want us to calculate big F prime of 3. That'll be F prime of g of 3 times g prime of 3. Now it's a game of plug and chug. When you do composition of functions, you work on the inside first. So that's what I'm going to do. What exactly is g of 3? So this will be f prime of, what's g of 3? Well, I come up here and g of 3 is equal to negative 7. So that'll be f prime of negative 7 times g prime of 3. Now I'm going to substitute in for that. What was f prime of negative 7? F prime of negative 7 was 2. G prime of 3 was negative 8. And then all I got to do now is crunch my numbers. 2 times negative 8 is negative 16, and that's my solution. Does that make sense? But you got to recognize this. And again, you can memorize this formula if you want to, but if you memorize the words, derivative of the outside, inside stays the same, times derivative of the inside, you can create the formula without having to memorize another formula for this class. Okay. Well, here's another one where word just loves to give you because they're trying to reinforce your idea. Because remember, way back when we talked about chapter 2.1 and 2.2, the geometric representation of the derivative is the slope of the tangent line. You have been programmed. Every time you think of derivative and you need a visual perspective, you draw in that slope of a tangent line. So what we got here is we got ourselves an interesting looking picture of bold graph g of x and a little check looking graph of f of x here. And they tell you up here that, quote, u of x is equal to f of g of x and v of x is equal to g of f of x. You are supposed to first find u prime of 3, and then you're supposed to find v prime of 3. All right? Well, before I find u prime of 3, remember, u of x was equal to f of g of x. Again, f is on the outside, g of x is on the inside. This is a chain rule. So take derivative of this guy. U prime of x would be equal to f prime, derivative of the outside, inside, g of x stays the same, times derivative of the inside, g prime of x. Okay, so far so good. But now, I had to write out my formula, but now I got to plug in my number. So this will be u prime of 3, which would be f prime of g of 3 times g prime of 3. So if you'll notice, it's exactly what the problem we just did a few seconds ago. Except for now, I got to plug in my numbers, and they didn't give me any numbers. They gave me graphs. So here we go. I'm going to work on the inside first, g of 3. So I'm going to go to my g function. Here is 0, 1, 2, 3. To get the coordinate, you got to get the y coordinate. So this is a y coordinate, 0, 1, 2, 3, 4. So g of 3 is equal to 4. So this becomes f prime of 4 times g prime of 3. Does that make sense? All I did was went to my g function. There's 0, there's 1, 2, 3, and then I graphed it and found the point. 0, 1, 2, 3, 4. G of 3 is equal to 4. Now, here we go. I want to know what f prime of 4 is. You'll notice these are very rigid functions, so it should be easy to figure out the derivative, which is the slope of the tangent line. But now x is equal to 4 here, so that's 0, 1, 2, 3, 4. There's 4 right there. I'm going to go plot the point, but I don't want the y coordinate. I want the derivative, which is the slope of the tangent line. What kind of slope of the line does this have? Well, there's a point. There's another point right there that it actually goes through the grid mark there. So I had to rise 2, run 1, right? Slope is 2 over 1, which is 2. Now I need g prime of 3. So here's 3 right there. There's g of it, but the slope, what's the slope of this line? I had to go down 1 over 1. And a down 1 over 1 makes a slope of negative 1. And so my answer is negative 2. Does that make sense? Using the slopes to get my derivative. Yeah?
If you had to find g prime of 2, how would you do that since the slope is different on either side?
G prime of 2. There's 2. G prime. Oh, that's real easy. What kind of point is that right there? Got a fancy name if you remember way back when in chapter 2 point something. It's a vertex. We also called it a cusp. And the derivative does not exist. So if I ask you what is g prime of 2, the answer is DNA does not exist. So they'll have to avoid 2 on this one. They'll also have to avoid 1 and -1 and f prime of 2 down there too. All these sharp terms, no derivatives exist. Let's look at the next one, v prime of 3. But this time they tell me v of x is equal to g of f of x. So again, chain rule, derivative of the outside, inside stays the same time, derivative of the inside. So v prime of x, will derivative of the outside, g's on the outside, so that'll be g prime. The inside f of x stays the same, but then you got to do times the derivative of the inside, that'll be times f prime of x. So for me to calculate v prime of 3, that would be g prime of f of 3 times f prime of 3. So that'll be g prime of, and now I'm going to go back to my graph, and I got to figure out what f of 3 is. Well, here's 0, 1, there's 2, 3, and see f of 3, f is the little thin line here. What's f of it? Well, they didn't ask for the derivative, they wanted the functional value. Well, the function happens to cross the x-axis. What does that make the y-coordinate? 0 times f prime of 3. This becomes a nice answer on this one because now, what is g prime of 0? Well, here is 0 right here, and I look at it, and you notice right there at 0, g of x has a horizontal tangent line. And what's the slope of a horizontal tangent line? 0, so that would be 0 times, this is just now for good practice, whatever f prime of 3 is. Let's figure out f prime of 3. Well, here's 0, 1, 2, 3. This is the line right here. I went through this point. I also go through this point, so it's that. What's the slope of the tangent line of that guy? Well, I have to rise 2, run 1, so that happens to be 2. But nevertheless, what's 0 times 2? That's 0, so the answer is still 0. There you go. Does that make sense? Again, everybody's got one. Looks just like this one on WebWork for using the graphs to figure out the derivative of these compositions. All right, number 21 here says this. Big F of x is equal to f of x to the 6. G of x is equal to parentheses f of x, close parentheses, raised to the 6. You also know that a to the 5th equals 11, f of a equals 2, f prime of a equals 8, and f prime of a to the 6 is 15. Your mission, find f prime of a and big f prime of a and big g prime of a. So first thing, before I find big f prime of a, I got to figure out what f of x is. Well, f of x was f of x to the 6. Pause, hesitate, and ask yourself, what do you see with this notation? I see f as the function on the outside, but inside that parentheses, I see x to the 6. This is outside, inside, this is chain rule. So to take derivative of this guy, big f prime of x, you take derivative of the outside, f prime. The inside x to the 6 stays the same, but then you got to multiply by the derivative of the inside. What's the derivative of x to the 6? 6x to the 5th. Does that make sense? But now, this is not, they didn't want big to calculate big F prime of x. They want a big F prime of a. So big F prime of a would be equal to f prime of a to the 6 times 6 times a to the 5th. All I did was replace all my x's with a's. Now, I'm going to go grab the chart over here, and let's see what we got. F prime of a to the 6. They gave me that one. What number was that? That was 15. Times 6 times, and they also gave me what a to the 5th was. What's a to the 5th? 11. And you notice I went and grabbed my handy dandy calculator here. So here we go. Multiply this. 15 times 6 times 11 is 990. This is the solution. Does that make sense? Again, another Weberberg problem. You got one just like it. Now this one, I'm going to do the same thing, but this was g of x. G of x was equal to f of x raised to the 6th power. So once again, I see chain rule. I see f of x literally on the inside now, and that 6th power on the outside. That's the trick, is to pause, hesitate, and see what you see, and see what location they are. Outside, insides, that's chain rule. So let's take derivative. G prime of x would be equal to, well, 6 is on the outside, so derivative of something to the 6th power, you bring down the 6. The inside f of x stays the same, raised to the 5th power. Derivative of the outside, inside stays the same time. Derivative of the inside is f. So the derivative of that would be f prime of x. So now I'm going to do the same thing by replacing all the x's with a's. So g prime of a would be 6 times f of a to the 5th times f prime of a. That'll be 6 times, and what's f of a equal to? Well, coming back up here, f of a was equal to 2. That's being raised to the 5th power, times f prime of a. And f prime of a was equal to 8. So what I ended up getting here was 6 times to the 5th times 8. So I'll put that on the old calculator. 6 times 2 to the 5th, over arrow, times 8. I get 1,536. Does that make sense? If I lose you guys anywhere. Question? Okay. Well, section 2.6. Now, up to date, we have been really nice to you guys. Every time we've asked you for a derivative, we've given you, y equals f of x. Y equals 3x squared plus 2x minus 5 cosine of x, or something weird like that. Okay? We always gave it to you as y equals or f of x equals and take derivative. But what if we can't get the function in terms of y? So that's what I basically am talking about over here. In previous weeks, we've been talking about, y equals f of x, and we talked derivative. That'd be y prime is f prime of x. You can also call that y prime dy over dx. So if I give you something like x cubed plus 2x and say take derivative, well, derivative of y is y prime. You can also call it dy over dx is equal to, you just take derivative. Derivative of x cubed is 3x squared. Derivative of 2x is 2, and I'm done. Okay? But what we're interested in now is what if I give you guys relations instead of functions? And what I mean by relation is that I got such a nasty looking equation here that it becomes to be difficult to be able to solve for y. Now in this example, yeah, it's not too bad because I got x equals x cubed plus 2x minus y. Okay, the y is intermixed with the x's, but you can actually solve for y. I can move the y over here, subtract the x, and I get this equation, y equals x cubed plus x, and the derivative of that would be clearly 3x squared plus 1, and I'm done. But that's not the way of the world. So this idea of what we call implicit differentiation is this. What you have here is an implicit equation. I've got x's embedded with my y's, all intermixed, and there's no way for me to be able to solve for y on the thing. I can't pull out a y and put y equals something in terms of x. The x's and y's are intermixed to each other, and we want to take derivative of these things. So I tried to talk about a derivative over here, and here is the big deal in terms of my relations here. So I've got this guy here. I've got x equals x cubed plus y squared. That is an implicit relationship, implicit equation with x and y, because you can't solve for y. Well, I know somebody wants to argue with me. Yeah, Dr. Taylor, I believe you can. You can. Go for it. Well, I would subtract x cubed from both sides. Well, knock yourself out. X minus x cubed equals y squared, right? Now what you going to do? What kills off a square? Take square root of both sides, of course. So y equals the square root of x minus x cubed. Only problem with that is this. When you take a square root of a problem, which one do you want? Plus or minus? And the problem doesn't tell you, and I'm not telling you, because basically you don't know. And because you don't know, you can't actually solve for y. Because as sure as you say I wanted the positive one, I'm going to say, no, maybe you wanted a negative one, and I'll mess you all up. Okay? So you can't get y by himself because of that plus or minus issue. This is called a relation and not an equation. It's not a function, excuse me. It's a relation equation. It's not a function. So this thing's going to violate the old vertical line test problem here in the old days if you actually try to graph this thing. But that doesn't matter. We're still interested in figuring out what the derivative of y is with respect to x. And that's the way you need to think of it. Y is a function of x. So what you're going to do here is we're going to start using more Leibniz notation with this material, but we're going to take the derivative with respect to x. So when you take derivative of x's, they're going to work the natural way you want to. But when you take the derivative of y, you got to think y is a function of x. And because of that, you're going to have to use the chain rule version of this thing. This is why this section follows the chain rule section. So let me show you. What's the derivative of x with respect to x? What's the derivative of x? 1. Yeah, equals, what's the derivative of x cubed with respect to x? Well, it is an x. So what is that? 3x squared plus, what's the derivative of y squared? Well, you're right, it's 2y, but the problem is y is a function of x. So you can use the chain rule. Chain rule is you took the derivative of the outside, inside stays the same, but then you got to do times the derivative of the inside. What is the derivative of y with respect to x? That's where you get the dy over dx Leibniz notation. Wrong. Every time, so here's a rule of thumb here. When I'm doing this implicit differentiation, every time I take a derivative of y, I'm going to multiply by that dy over dx. You take derivative of x's normally, but every time you take derivative of a y variable, every y variable has to be multiplied by times dy over dx, and it comes from the chain rule of the derivative of the inside. But now comes your algebra. This is the derivative equation. Now your mission is you have to solve for the dy over dx. So to solve for this thing, I'm going to subtract 3x squared from both sides. That'll cancel. That'll give me 1 minus 3x squared is equal to 2y dy over dx. Now I'm going to divide by 2y on both sides. What I do to one side, I do to the other. And that gives me, this would cancel. This would leave me with dy over dx is equal to 1 minus 3x squared divided by 2y. And you see, the original equation was implicit, meaning I had x's and with y's all intermixed, and my derivative will also be implicit. I'll have y's inside with my x's in my derivative. Well, that's only fair since it was an implicit equation, and this is my solution. And if you look over here someplace, maybe the next page over, you'll see, yep, there it is, same answer. There you go. All I did was try to type it up for you guys. So here's another one right here. So, and I'm just going to actually I try to type it up for you guys so you can try to follow through, but sometimes it's better just to somebody give you a problem and you just kind of walk it over together. So here's another implicit equation. X is equal to 4x cubed plus y squared minus 8y. Another problem, impossible to solve for y because it is a y squared and the old square root plus and minus problems here. So it's an implicit equation. So your mission, I want you to find an implicit equation for the derivative dy over dx, which represents your slope of your tangent line. Okay? So what I'm going to do here is take my equation, and of that entire equation, I'm going to go d over dx. This is that Leibniz notation, meaning take the derivative of the entire equation that follows with respect to x. So you take derivative of x as normally, but every time you take a derivative of y, you got to multiply by dy over dx. So what is the derivative of x with respect to x again? 1. Keep the equal to in the same spot and move on the other side. What's the derivative of 4x cubed? 12x squared plus, here it comes, what is the derivative of y squared? 2y, chain rule, times derivative of the inside, times dy over dx. Every time you take derivative of y variable, you've got to tack on that dy over dx from the chain rule, derivative of the inside. I'm not done yet. Minus, what's the derivative of 8y? 8, but it's a y variable, so you got to tack on that times dy over dx. Every time you take derivative of a y variable, you got to tack on that times dy over dx because you're taking derivative with respect to x, not with respect to y. Does that make sense? Now, as I mentioned before, you got to solve for dy over dx. So now comes your algebra. So solve for dy over dx. So I'm going to subtract 12x squared from both sides. That gives me 1 minus 12x squared, this would have canceled there, equals 2y dy over dx minus 8 dy over dx. What do you notice? Well, remember, when you're solving for dy over dx, you get all the terms with dy over dx on one side and all not terms that don't have a dy over dx on the other. And here's the big word right here. I got multiple terms with this dy over dx. So what am I going to do? Factor. This is how you take multiple terms and get one term out of it so you can solve for it. I'm going to factor out the dy over dx. That gives me 1 minus 12x squared is equal to, parentheses, 2y minus 8 times dy over dx. And what's the last move I got to have to be able to solve for dy over dx? I'm going to divide. And that's going to give me dy over dx is equal to 1 minus 12x squared divided by 2y minus 8. And I made it a little small there, but yep, that's the same answer as I got before. I divided to solve for the dy over dx. So let's look at one more of these kind of problems down here. So here's one, and these are the problems I did on the awesome pre-section video, so I will allow you to go and watch those things again and make sure you take good notes off of it. But this problem here was a little more difficult. So I want to look at this one. You got the implicit equation, x is equal to x cubed times y squared minus 3y cubed. Again, same mission. Your job, find y prime or dy over dx or a function for the formula for the slope of the tangent line, whatever the case may be. Here we go. First thing I'm going to do is, when you have an implicit equation, just jump in with both feet and just start taking the derivative with respect to x. So to denote that, put little brackets around the thing and put a little dy over dx. Okay? So what is derivative of x with respect to x? 1 equals, what is derivative of x cubed times y squared with respect to x? And what rule would I have to use? That's very good. Try to give you guys a hint. You're taking the derivative of x cubed times y squared. There's a big old times in the middle of these two guys. So take the derivative of this guy, you've got to use the product rule. Product rule, derivative of the first times the second plus the first time derivative of the second. Derivative of the first, what's derivative of x cubed? 3x squared. Derivative of the first times the second, y squared, plus the first, x cubed. Now help me out here, times derivative of the second. What's derivative of y squared? 2y, you're getting it, times dy over dx. Every time you take derivative of y, you got to tack on that dy over dx. So there's the derivative of x cubed times y squared minus, what's derivative of 3y cubed? 3 times 3 is 9. Y squared what? Dy over dx. And again, I got multiple terms with the dy over dx in it. So to solve for this, I'm going to move the term without the dy over dx in it to the other side. So I'm going to subtract 3x squared y squared from both sides. That gives me 1 minus 3x squared y squared equals, this cancels. And I'm going to clean this up. That'll be 2x cubed y dy over dx minus 9y squared dy over dx. Again, I have multiple terms with a dy over dx in it. The trick is always to be able to solve for that dy over dx, I got to factor it out. So this gives me 1 minus 3x squared y squared equals, parentheses, 2x cubed y minus 9y squared times dy over dx. I factored out the dy over dx. And then I got one more move to make to solve for dy over dx. I'm going to divide by 2x cubed y minus 9y squared, divided by 2x cubed y minus 9y squared. This cancels, leaves me with dy over dx equals 1 minus 3x squared y squared divided by 2x cubed y minus 9y squared. Now, one last thing on this problem. I have seen students, very, very bright students, take this ball and run all the way down the field with it. And they fumble at the goal line. because they chunked this problem on a multiple choice kind of an answer. And the problem is this answer is not in the multiple choice section. So you got to be able to outthink the box. What's another way I could have written this guy? Or dy over dx is equal to 3x squared y squared minus 1 divided by 9y squared minus 2x cubed y. That would have been the answer that they would have put on the multiple choice, just to see if you actually can figure out the math. What did I do? What did I do from the first one to get the second one? Yeah.
On the bottom, wouldn't it be negative 9y squared plus?
Nope. What did I do? That's the question. Once you see what I did, you'll see what I did.
Did you factor in a -1?
Very good. I factored out a -1 out of the numerator, and I factored a -1 out of the denominator. Okay? This is a trick on the final exam that they like to do, just to, in terms of multiple choice answers. If your answer isn't there, that doesn't mean it's wrong. It usually does, but it just may not be wrong. So maybe they did some kind of algebra trick to this thing. And this is one of your classic algebra tricks. If I factor a negative out of the numerator, it changes the signs. And I always like to put the negatives in the back. Does that make sense? That's why this becomes the -1 here, and that negative got pulled out. But it would have canceled with pulling a negative out of the bottom, putting the 9y squared out front, and making the 2x cubed y a negative in the back. And that's how they got the answer. Just a thought for you guys in terms of what can they do to this problem. Now, if you look at my wonderful math, you'll know I got the exact same answer that I did over here because I did it the same way. But don't forget this little trick here. Now, again, watch the awesome pre-section videos for these couple of problems here. And if you'll notice, over here with number 4, well, they make you jump through one more hoop here. And that is, find y prime and evaluate it at a point 2, -1. Well, all you do at the end is basically replace x with 2, y with -1, and just crunch it out. And actually calculate what the slope of the tangent line is. Okay? So, let's pick it up with number 5. Directions are all the same. Find the implicit derivative. So, I'm going to take my equation, x squared plus 12y squared minus 11 equals 0, and I'm going to take the derivative with respect to x. Now, here we go. What's the derivative of x squared with respect to x? 2x. Plus, what is derivative of 2y squared with respect to x? I hear 4y mumbling here. What else? Thank you. Be proud. dy over dx. Yeah. 4y times dy over dx. Minus, this is for your benefit, what's the derivative of 11? Yeah, it goes away. 0. Equals, and this is important. What's the derivative of 0? Still 0. It's not the same thing. You're not just setting it equals 0. It's the fact that the derivative of 0 is 0. Okay? Technicality here. So this makes an easy equation here. So I'm going to subtract 2x from both sides. So that gives me 4y dy over dx is equal to -2x. Then I'm going to divide by 4y on both sides. And that's going to give me dy over dx is equal to -2x over 4y. And that's fine, but, you know, we're math people and we just can't handle that. Reduce your fraction. So what do you get? dy over dx is equal to -x over 2y. That's typically how they would have written it up in a multiple choice answer. Not too bad on the first one, of course. But look at the second one. The second one is one of these places that a lot of folks will make a careless error. So let me show you how to handle this kind of problem. First off, let's read the problem. I've got here y squared times x minus 5y divided by x plus 1 plus 3x equals 4. Your mission, find implicitly the derivative of dy over dx. So I'm going to take my equation, y squared times x minus 5y divided by x plus 1 plus 3x equals to 4. And I'm going to put brackets around it and put d over dx. Take the derivative with respect to x of this entire equation. Here comes the trick here. This one's nasty, so let's play the game. What's the derivative of y squared times x? And what rule would you use? It's y squared hint times x. What rule would you use? Product rule. Product rule. Derivative of the first times the second plus the first times the second. Derivative of first. Derivative of y squared is what? 2y dy over dx. Every time you take derivative of y, you take on that dy over dx. That's derivative of the first times the second x plus the first y squared times derivative of x. What's derivative of x? 1. And I did that for your benefit so you can literally see the product rule. But now here it comes. It's minus 5y divided by x plus 1. What is that? Quotient. I got to use the quotient rule, but quotient rule is going to mess you up because look what's in front of it. It's a negative. Oh, okay. Just what you do when you're subtracting it. If it's plus, it's fine. But when it's a minus, you should do this. Make it a minus and put a big bracket because that negative is going to distribute. That's where most people forget to distribute the negative. Just leave the negative out front and then just focus on the 5y divided by x plus 1 quotient rule. Yeah.
Distribute the negative first.
Well, you could put the negative on top and call him negative 5y divided by x plus 1. You could do it that way, and that will distribute the negative throughout. But most folks would forget to do that. If they don't see negative 5, they see minus the entire fraction. And when you see that, just leave the minus there and put a bracket. It's the easiest thing to do. Now you can use the quotient rule on, you don't have to worry about the negative at all. Quotient rule, derivative of the top times the bottom minus the top times derivative of the bottom. What's derivative of the top? What's derivative of 5y? 5. Every time you take derivative of y, you got to tack on that dy over dx. So derivative of 5 y is 5 dy over dx. Derivative of the top times the bottom, x plus 1, minus the top, 5y, times the derivative of the bottom. What's the derivative of x plus 1 with respect to x? 1. All over the bottom, x plus 1 squared. Words are going to be nasty looking, but this is why I took the negative out front and put him in a bracket out there. So I could just literally the quotient rule. The derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. Let's keep going. Plus, what's the derivative of 3x with respect to x? 3 equals, what's the derivative of 4 with respect to x would be 0. Now, what am I going to do to this thing? I'm going to clean him up. Watch how I clean him up. Well, 2y dy over dx times x looks so much better to write it as 2xy dy over dx plus y squared times 1 is just y squared minus, now leave the bracket here. Here's the trick. Cleaning them up. This is a big quotient rule, and you want to clean this guy up. You should take your denominator and put it under each term in the numerator. You're going to basically break up your fractions. That's going to give you 5 times x plus 1 times dy over dx over x plus 1 squared minus 5y times 1 over x plus 1 squared, close bracket, plus 3 equals 0. And I'm not done yet, because inside my parentheses, you see that 5 times x plus 1 times dy over dx divided by x plus 1 squared. Somebody canceled. What cancels? X plus 1s. One of those guys cancels. So this leaves me with 2xy dy over dx plus y squared minus bracket 5 dy over dx times x divided by x plus 1 minus 5y divided by x plus 1 squared, close bracket, plus 3 equals 0. If you'll notice what I'm doing here, I'm not skipping a step. I'm making sure you guys can follow this, because one false move will make this problem all wrong. So I've cleaned up inside my parentheses, and I've created two fractions. Now this negative is going to distribute. That's going to give me 2xy dy over dx plus y squared minus 5 over x plus 1 dy over dx plus, a negative makes it positive, 5y over x plus 1 squared plus 3 equals 0. And all I did was I just cleaned up my fraction. I put the dy over dx in the back. It just looks a little better that way. This is all cosmetic right now. What's your mission on every one of these problems in section 2.6? Solve for dy over dx. Well, how do you solve for dy over dx? You get all the terms with dy over dx on one side, and you move all the other terms to the side. So all the terms without a dy over dx. Well, this one has a dy over dx. I'm going to leave them there. The y squared does not. So I'm going to subtract y squared from both sides. This has a dy over dx on it, but this one doesn't. So I'm going to subtract the 5y over x plus 1 squared minus 5y over x plus 1 squared. And the 3 doesn't have a dy over dx on it, so I'm going to subtract 3. So this cancels, and this cancels. This leaves me with 2xy dy over dx minus 5 divided by x plus 1 dy over dx, okay, is equal to negative y squared minus 5y divided by x plus 1 squared minus 3. Did I lose you guys anywhere? Now I'm juggling, getting all the terms with dy dx on one side and the non-dy dx terms on the other. What's my next move? Factor. I'm running out of room on this one. So what I'm going to do is the famous factor like I was on the blackboard thing here. I'm going to mark through it, put brackets around it, and watch. I pulled out the dy over dx. There we go. I factored it out. Now what's my last move? To divide. And this is going to give me dy over dx is equal to negative y squared minus 5y divided by x plus 1 squared minus 3 divided by, this whole term goes to the denominator, 2xy minus 5 divided by x plus 1. And as nasty as that is my derivative. And of course, problem number 45, page 207 on your next test says this. Find the slope of the tangent line at the point 2, 1. Well, what am I going to do at the point 2, 1? I'm going to take x is 2, chunk in there, y is 1, chunk in this thing, and crunch out a numerical value. And that numerical value will give me the slope of the tangent line at that point. Does that make sense? Questions? Speaking of that, let's take a look at number 7. Now, I know a lot of people sit there and talk and go, you know, Dr. Taylor, you're kind of being a German on this thing here. Always using these dy over dx's for using for the derivative and stuff. And when I'm doing implicit differentiation, you're right. I always use dy over dx. I could use y prime, and tell you what, just to make you guys happy about it, I'll use a dy over dx. I'll use a y prime instead of dy over dx in this problem. Because here's the problem. This is a simple problem. Find y prime for 2y plus 5 minus x squared minus y cubed equals 0, and then evaluate it at the point 2, negative 1. Because I want to show you why I don't want to use y prime. Here we go. So I'm going to take the derivative with respect to x of this equation. 2y plus 5 minus x squared minus y cubed equals 0 first. And then I'll do part 2, evaluate it later. Okay? Well, on your mark, get set, go. What is the derivative of 2y with respect to x? Derivative of y would be dy over dx, but you guys want me to do the y prime thing like the book does. Fine. There it is. 2 times y prime. Derivative of y would be y prime. Okay? Plus, here we go. What is the derivative of 5? 0. Okay, good. Minus what's the derivative of x squared? 2x minus what is the derivative of y cubed with respect to x? 3y squared. Chain rule, derivative outside, inside times derivative inside, but inside would be y, so you got to tack on instead of a dy over dx, a y prime. Okay? Equal to what's the derivative of 0? 0. Now, the reason I don't do this one is like you can look at this equation and see. I was very neat and very detailed and very oriented. Every time I took a derivative of y, I have to tack on that y prime on it. But you guys are slack and you do it at 90 miles an hour because you feel like you got someplace to go after class or something or other. I'm not really sure, but you understand, I can do this thing, and I give you one of these really nasty equations. All you got to do is misplace one of these little primes, and all of a sudden that y prime becomes a y, and that becomes a completely different kind of a problem. Does that make sense? This is why I don't do y prime. dy over dx just stares you in the face. Granted, it's very German, it's Leibniz notation, but it just stares at you in the face. You can find where these derivatives are located at without much difficulty. But if I got a large equation, I'm taking derivative of y's over here and y's over here, I got y prime here, y prime, I could lose a prime. And if I lose one prime, I've got the whole problem wrong. That's why. But I was very neat and orderly on this one. So I'm going to solve for y prime. So I'm going to add the 2x to both sides. That's the only non-zero term without a y prime in it. That gives me 2y prime minus 3y squared times a y prime equals 2x. I'm going to factor out the y prime out of the thing. That's going to give me a 2 minus 3y squared equal to 2x, and then I can divide. Y prime is equal to 2x divided by 2 minus 3y squared. And there is the answer for the first part. Does that make sense? But now they want it as the second part of this one. The second part of this one is you're supposed to take your y prime and evaluate it at the point 2, negative 1. X is 2, y is negative 1. This will be equal to 2 times 2 divided by 2 minus 3 times negative 1 squared. 2 times 2 is 4. Divided by 2 minus negative 1 squared is 1 times 3 is 3. And so that's 4 divided by 2 minus 3 is negative 1. So the answer is negative 4. In other words, the slope of the tangent line, which is your derivative evaluated at the point 2, negative 1, is actually equal to negative 4. Does that make sense? Because you and I both know where they're going to go with this stuff at. And let me explain it to you. What are we really doing here? This is what we're doing. In chapters 2.1, 2.2, 2.3, 2.4, and 2.5, you've been given functions. You know, some of them have been kind of nasty. Maybe it looks something like this. Here's old y equals f of x function. And they say, all right, find the equation of the tangent line at this point x equals, I don't know, 5 or something like that. So I'm going to come over here and plot him. So this is the y coordinate of this guy. And then we were supposed to come up here, grab this line, and it keeps on going like this. And we're supposed to find the equation of the tangent line at that point. How many times have we found the equation of a tangent line in here? And by after web work, probably hundreds. Okay? How do you find the equation of the tangent line? What? Anytime you find the equation of a line, what do you always got to use? Point slope. So we had to use the old point slope formula. Y minus y1 equals m times x minus x1. They gave you the x. You had to calculate the y, so you got your point. So you're going to have this point x1, y1 right there. Okay? And then you had to find the slope of the tangent line. But the slope of the tangent line was the derivative evaluated at your x number. In this case, it was 5. And so you plug it into this formula, and you actually found the equation of the tangent line. That's what we've been doing. But now we're in section 2.6. This is what's going on now. For you see, this was a function. For you see, we're talking about relations, non-functions, you know, things that look like this. There it is. That is what x embedded with y looks like when they're on inside of each other and stuff like that. Y is in terms of x, but you can't solve for y because it's it's not a function. It violates the vertical line test. But you know what your job is? We got some kind of crappy looking equation for this guy. We're going to pick a point right here. I'm going to have to give you both coordinates here. We're going to give you an x1 and a y1. And we're going to tell you, find the equation of the tangent line right there of this particular relation. So what do we got to have? We got to have the slope of the tangent line, which is going to be this dy over dx evaluated at this x1 comma y1 guy, right? And there's my slope, there's my point, and we're going to still use the old point slope formula, y minus y1 equals m times x minus x1. It's just going to be a little bit more to-doings for us to actually find the derivative because it's going to be implicit. This is what's going on. You can still find the equation of that tangent line as long as you know the point that goes through that relation. Does that make sense? So, I'll do an example of that in a little bit, but the other thing is this. We're going to be focusing also on variables. Every problem we did up to date, including this example right here, was y was a function, let me put it up here, y is a function of x, or you have basically a relation x, f of x, y equals some kind of weird constant or something like that. That's what this equation is. Does that make sense? So, now, we're talking about x and y's. But are x and y the only variables in the universe? Oh, no. So, here we go. We're setting you up for chapter 2.7, by the way, just in case you want to know. A equals pi r squared. What is this an equation of? You should know it. It's kind of engineering classic. It's the equation of a circle, area of a circle, right? You're supposed to find dA over dt. Well, what's t? Time. I don't see time in this equation. Exactly. So here's the trick. When I had the other problem and I was doing derivative with respect to x, when you had an x, you just took derivative of it normally. But every time you took a derivative of a y variable, which wasn't x, you had to tack on that dy over dx. You're taking derivative with respect to t. So every time you take a derivative of any variable, you've got to tack on a d variable over dt. Okay? So, a equals pi r squared. You're going to take the derivative with respect to time. But there is no time variable in this equation. Don't care. Every time you take a derivative of any variable, you've got to tack on that d variable over dt. So what's derivative of a with respect to t? dA over dt. It's derivative. A is one variable. It's 1 dA over dt. Equals pi. 3.141599269. Yeah. It's a number. It's a constant. It holds over. What's derivative of r squared with respect to t? Well, derivative of r squared is going to be 2r, but it's the chain rule. That's the derivative of the outside. Inside stayed the same, but then you got to do times the derivative of the inside. What's the derivative of r, listen to my words, with respect to t? Times dr over dt. And you can clean this up, and you got your first related rate equation. dA over dt is equal to 2 pi r times dr over dt. And so, how nasty can this kind of stuff get? Well, wait. Look at the next one. We want you to find dv over dt for v equals 1/3 pi r squared h. Okay? Do you guys happen to know what the equation is of 1/3 pi r squared h is? You know what V stands for, right? Volume, okay, I'm just checking with you guys. R stands for radius, H stands for height. What is the height and radius of what? Very good. Volume of a cone, and what we call a right cone. This is the volume of a right cone. Just in case you wanted to know, it looks like the dunce cap. There it is. The right cone, where this is the height, perpendicular, and this would be your radius. Does that make sense? This is the volume of a cone. We want you to take the derivative of this cone with respect to t. But here's the deal. Every time you have a variable, you got to tack on that d variable over dt. So you got to be careful. So here we go. So to take the derivative of, with respect to t, of v equals 1/3 pi r squared h with respect to t. Well, what's the derivative of v with respect to t is going to give me dv over dt equals 1/3 pi is a what? 1/3 is 0.333. It's a constant. Pi, 3.1415926. Yeah. It's a constant. So those guys hold over. 1/3 pi. Now, I've got r squared times h. How do I take the derivative with respect to t of r squared times h? Product rule. Derivative the first times the second plus the first times the second. What's derivative first? What's derivative of r squared with respect to t? Well, we just did that a few seconds ago. That would be 2r dr over dt. Does that make sense? That's derivative of r with respect to t. Derivative the first times the second times h plus the first r squared times derivative the second. What's derivative of h? 1. But then you got to tack on that times dh over dt. And if you want to, you can distribute just to make it look good. And you got your equation. dv over dt is equal to 2 pi thirds r dr over dt times h plus 1/3 pi r squared times dh over dt. That is the derivative of the cone with respect to time. And these dr over dt's talk about the rate of change of the radius. dh over dt stands for the rate of change of the height. And we're going to start getting into word problems with this stuff. Does that make sense? Setting you guys up. But it's still an implicit style problem because these variables are embedded. You're not taking derivative with respect to the variable. You're taking derivative with a different variable, time.
You have to distribute?
No, you don't have to, but trust me, later on, I know the word problems. Yeah, you're going to want to eventually. Yeah. Here we go. Here's another one. If f of x plus x to the 7th times f of x cubed equals 11 and f of 2 equals 6, your mission, find f prime of 2. All right. F of x plus x to the 7th times f of x raised to the 3rd power equals 11. We're supposed to take derivative and find it. What does f prime of 2 actually mean? Well, it means it is df over dx evaluated at 2. It's the derivative. So what I'm going to do here is, first off, before I plug in x as 2, I'm going to sit there and take derivative with respect to x on this thing. All right, so here we go. What is the derivative of f of x? What do you call it? The derivative of f of x. Oh, fine. We'll do f prime. F prime of x plus, what is the derivative of x to the 7th times f of x cubed? And what rule would I use? Well, I got two things going on here. I see a product and I see a chain because f of x is on the inside, cube's on the outside. But what's the big picture? Let me read it to you. You can figure it out. X to the 7th times f of x cubed. What's the big picture? Product rule. Big old times in the middle of it. It's a product rule. Okay? And if you get in trouble, you literally just read it, hopefully in your head, not during a test. People get mad at you and hurt you. But actually just read it to yourself and you can see, okay, what's the big operation in the middle? It's a product. So product rule. Derivative the first, derivative of x to the 7th would be 7x to the 6th times the 2nd, f of x, quantity cubed, derivative the first times the 2nd, plus the first, x to the 7th times derivative the 2nd. What's derivative of f of x cubed? Well, that's chain rule. The 3 pops out front, the f of x inside stays the same, squared, but then chain rule. Derivative the outside, inside stays the same, times the derivative of the inside, times f prime of x. Equals, what's derivative of 11? Yeah, don't forget that. How many people just keep setting it equal to 11? It's getting it up. No, derivative of 11 is 0. So there's my answer right there. But what are we after? We're not after this dude. We're after f prime of 2. So now at this point, I'm just going to go ahead and plug in x is 2. This will be f prime of 2 plus 7 times 2 to the 6 times f of 2 cubed plus 2 to the 7th times 3 times f of 2 squared times f prime of 2 equals 0. What did I do? Every x, I chunked in a 2. We're supposed to find f prime of 2. So that's going to be my variable. But coming up here, they gave me some information. What is f of 2 equal to? 6. So I get to replace that. So f prime of 2 plus 7 times 2 to the 6 times, there's an f of 2, but that's equal to 6 cubed plus 2 to the 7th times 3 times, oh, there's another f of 2. That'll be 6 squared times f prime of 2 equals 0. Well, now I'm going to crunch some numbers. This is f prime of 2 plus, what is 7 times 2 to the 6th times 6 cubed. Yep, gotta love it. 96,768. Yep, I stole this one right off Weber. 96,768 plus, let's put this one on there. It's 2 to the 7th times 3 times 6 squared. Yeah, I know that's 36, but I'm putting it on a calculator anyway. 6 squared, and that is 13,824. 13,824 f times f prime of 2 equals 0. Your job is to solve for f prime of 2. This right here is where people get it down to until they fumble the ball at the goal line. You're there at the goal line. Solve for f prime of 2. Here's your problem. If I tell you this, what is 3 f prime of 2's plus 4 f prime of 2's? How many f prime of 2's do you have? Let's try again. 3 f prime of 2's plus 4 f prime of 2's. 7 f prime of 2's. What do? When you're adding, you just add the coefficients up front, right? If I go, what is 3x plus 2x? It's 5x. You just add the coefficients up front. How many f primes of 2's do you have right here? Understood to be 1 of them. Plus, you got 13,824 f prime of 2's. How many f prime of 2's do you actually have? 13,825 f prime of 2's plus 96,768 equals 0. That right there kills students for some reason. They can handle 2 f prime of 2's plus 3 f prime of 2's. They can do that. But once I do 1 f prime of 2 plus 13,824 f prime of 2's, they fall to pieces on that one. Okay? Now, how am I going to solve for this thing? I'm going to subtract 96,768 from both sides. That gives me 13,825. F prime of 2's equals negative 96,768. And then I'm going to divide by 13,825. Gotta love web work here, but it's nothing but arithmetic. So the answer is f prime of 2 is equal to negative 96,768 divided by 13,825. I don't think it reduces, but I don't remember, so let's try it out. Negative 96,768 divided by 13,825, and can convert it back to a fraction. Yeah, it actually does reduce a little bit. It reduces to negative 13,824 over 1975. But you know what? Web work doesn't care. Just chunk that sucker in there and you'll be happy about it. Does that make sense, though? Did I lose you guys anywhere on this one? All right, I got 2 minutes. One more problem. All right, here we go. No, I got to pass back the test. I forgot about that. So let me pass back that. I'll finish this problem next time. I'm one section behind where I'm supposed to be, or one problem behind, and I'll do 2.7 next time. So let's. I got to pass back the test. So let's do that.